This is geometry, level 1, the basics that you need to know for geometry. Let's begin by talking about a line segment. A line segment is a series of points on a straight path that connect two endpoints together. So AB is a segment or a side, and it's marked by a little symbol, a segment symbol above the two letters. Every line segment has a length, and on my computer from A to B is about 6 centimeters. There are many points on a line segment, but there is one very special point called the midpoint. It's the point that's exactly halfway between both endpoints. So in this particular picture, AM would be the same length as AB. They both would be 3 centimeters long. Midpoints make two equal segments. That is one of the definitions that you need to know. Looking at this next picture right here, we have a angle, and what I can do with this angle on my computer is I can make it larger or smaller. Angles describe the amount of opening that exists between two segments or two rays or two lines. And right here I've got a very, very small angle, maybe about 1 degree. As I open it up, it becomes bigger and bigger, and it's an acute angle right now, someplace between 0 and 90 degrees. Right about there is maybe 50 degrees, 60, 70, 80 degrees, and then finally a right angle at 90 degrees. If I open it up more than 90 degrees, I get an angle that's between 90 and 180 degrees. That's an obtuse angle, and I can make the angle as large as I want. And if I lay it out where it's completely flat against the original, I'll have 180 degrees. You don't have to keep on bending it back beyond that. That would be a reflex angle. But the main idea from this slide to get from me is that an angle describes how much of an opening there is. It's useful to think about an angle as a mouth that's opening and closing. I mean, if this is an alligator's mouth and that's how wide it's not opened at a very large angle. Maybe that's like 8 degrees, 10 degrees. The alligator opens its mouth larger and larger. The angle size is getting larger. So that's the idea of an angle, is the opening, the size of the opening. When you name an angle, very, very important, for this picture right here, for this opening, the angle is called angle CDE. From C to D to E forms the angle. You may also call it in reverse EDC. When we name an angle, you can name an angle with 3 letters almost all the time. Sometimes you can name the angle with just a single letter. So for this example right here, I can get away with calling this just angle D because there's really only one angle there in the picture. And what I often do in my class is I'll highlight the angle with a little arc like that to tell the student that we're talking about this guy right here. Sometimes I'll even number the angles to make them easier to talk about, and you'll see that on the video. So we might also call this one angle 1. If you number it to the side here, make sure you also number it in the picture. On this slide, I will show you how to create two equal angles by forming what is called an angle bisector. So cutting an angle in half is something we can do with a compass. So originally, let's say that this angle here is worth 46 degrees. I can create two 23-degree angles by taking a compass out and swinging it 3 times. Swinging from point D, I can swing an arc so that it creates 2 intersection points on the original angle. So that's one swing of the compass. I can move the point of the compass now to the top point and swing into the angle, and then move my compass point down below here and swing one more arc into the middle of the angle. Then I can actually connect from point D through that intersection point, which I can call F, to create an angle bisector. And angle bisectors make two equal angles. So this angle here would be 23 degrees, and this angle here would be 23 degrees. So that was one way to get congruent angles, was to take an angle and form an angle bisector that would split it into two equal angles. Another way, very simple way to get equal angles, is just to take two intersecting lines and find the angles that are across from them. And those angles would have to be equal to each other. So, for example, if this angle here was 85 degrees, this angle here would also have to be 85 degrees because they would have to be identical. And also, since two angles that make up a straight line have to make 180 degrees, this angle on the top would have to be 95 degrees. And then its matching vertical angle would be below it right here, also 95 degrees. So looking at this other diagram that I already have printed on the slide, shows some vertical angles there. And this is a quick proof of why those angles are identical to each other. So just to walk you through this, we know that angles 1 and 2 must add up to make 180 degrees. We also know the same thing is true about angles 2 and 3. And that is because linear angles, angles that make a straight line, must add up to 180 degrees. Since this is true, since 1 and 2 is equal to 180, and also we know that 2 and 3 is equal to 180, we could replace or substitute this 180 degrees with a replacement. And what could we replace 180 degrees with? In yellow here it says that 180 degrees could be replaced with angles 2 and 3. So we call that the substitution method, a way to replace equals with equals. And you can see by doing this move, I have angle 2 on both sides of this equation. I could subtract away that angle 2 from both sides, which proves that vertical angles are congruent. So angle 1 would have to be the same size as angle 3. And that is the proof of why two vertical angles are always equal. Another word for linear angles would be saying supplementary angles, and that's what this slide here is showing, that the vocabulary word that 1 and 2 could also be referred to as supplementary angles. So if this angle here was 30 degrees, its supplement would be 150 degrees. In terms of parallel lines is a very important concept. Parallel lines will never intersect to form vertical angles. And the symbol that we use for vertical angles is this symbol here, which looks exactly like what parallel lines do. They never cross. If we have parallel lines that are cut by a transversal is a line that goes through both parallel lines. So suppose that I created a transversal here that cuts through both of those lines. Once I've done that, that new line has created 8 angles altogether, and there are several angles here that are the same size. One way to begin is to talk about these two angles right here, which I'll label angle 1 and angle 2. Angle 1 is equal to angle 2 for a guaranteed fact. It's also a fact that angle 3 must be the same as angle 4, and it's for the same reason. We call those angles alternate interior angles. They're called interior angles because they are on the inside, in between the two parallel lines. They're called alternate interior angles because one angle is on one side of that transversal and the other angle is on the other side of it. They're alternating. And the same goes for angles 1 and 2. All right, with that transversal, the transversal can also help us find some other special angles. There's also corresponding angles. These angles right here, angles 1 and 2, are corresponding. They are in the same position, but at two different intersections. And those angles have to be the same size. Angles 3 and 4 also have to be corresponding. They also have the same angle measurement. And that's because parallel lines are traveling in the same direction. So angle 3 must be the same as angle 4. We also have angle 5 and angle 6 being corresponding. They're in the same position. So angles 5 and 6 have to be the same. And then lastly, angles 7 and 8 must be the same as well. When we have the transversal piercing through two parallel lines, we also have another set of special angles called consecutive interior angles. Angles 1 and angles 2 are different sized angles. They are not necessarily the same, but one thing that is always true is that they will add up to 180 degrees. They are interior angles because they live inside or in between the two parallel lines, but they are not alternate interior angles. They are living on the same side of the street, so they are called consecutive interior angles. Also, angles 3 and 4 would also be considered consecutive interior angles. Perpendicular lines. A very important thing to know. Perpendicular lines make two equal right angles. It's often confused with parallel lines. The symbol for perpendicular looks just like it would in the actual picture. That together, the two segments are forming a picture that looks just like the symbol is showing. And in that symbol, those two angles are 90 degrees, and in the picture, we're getting 90-degree angles. Sometimes two of them, possibly one of them. And in this last question, on this picture over here, there's actually 4 right angles. That's what it means for two lines to be perpendicular. Perpendicular bisectors are special perpendicular lines or perpendicular segments. They make two right angles, and again we would write that with the perpendicular symbol. But another thing that we get with perpendicular bisectors is we also get two equal segments. So just because a segment is perpendicular to another segment or line, it doesn't mean that one will cut another segment exactly in half. But it's a different story with the perpendicular bisectors. We can make a perpendicular bisector by using our compass, and the technique that I've been using in class is telling my students to open your compass more than halfway between the 2 points, the 2 end points, and place your compass down on the first end point and swing an arc across the segment. Then switch to the second point, point B, and swing another arc from point B with the same measurement on your compass. Then you can connect the 2 points that are formed from the top and bottom of those intersection points to create the perpendicular bisector. So that yellow line that I've written in there, I could nickname CD. And in this picture, you'd say that CD is perpendicular to AB. It also is a bisector. So this point right here that's on the original segment would be the midpoint. So as I wrote down below, the distance from A to M is also equal to the distance from M to B.